New Zealand's alpine environment reflects the powerful influence of tectonic and erosive forces. The collision of continental plates is pushing the mountains upwards, while the landscape is being torn down and sculpted by the effects of snow, ice, wind, water, seismic and volcanic events. Understanding the forces above and below New Zealand helps explain how this young land was formed. We will learn about some of the research and experiments used to investigate these forces. We will also explore the spiritual and cultural significance to Māori of the landscapes and the rumblings beneath New Zealand. Aoraki Mount Cook is the highest peak in New Zealand's southern Alps. The range of mountains dividing east and west coasts. Lifted high by the forces of tectonic plate movement.
The theory of plate tectonics has completely revolutionised the way scientists look at planet Earth. And here in New Zealand, we happen to be right on the boundary between two massive tectonic plates that are colliding into each other. I've come here to Aoraki Mount Cook National Park to have a look at how these spectacular peaks of the Southern Alps have been uplifted over the last 10 million years.
The Southern Alps run 500 kilometres north to south, characterised by sharp ridgelines, glaciers, valleys and lakes, all under constant attack by the forces of erosion.
The rocks that make up these mountains have a wild and tormented history. This area that we're standing in right now was actually under the ocean about 23 million years ago. At that time, these two huge plates started to collide, the Pacific plate on the one side and the Australian plate on the other. This collision compressed the Earth's crust and developed into what we now call the Alpine Fault. Along this fault, many earthquakes have pushed the land up to give these uplifted mountains around us today. 10 million years ago, this uplift really got going, but 5 million years ago, it accelerated even further. Now, in geological terms, that means that these mountains are actually still very young.
The mountains play a significant role in the climate and environment.
I'm climbing along the main divide of the Southern Alps, the backbone of the South Island. The melted snow that flows into the rivers on the left-hand side of that peak behind me will end up on the west coast, while the melted snow on the right-hand side will go to the east coast. This divides the South Island into two separate geographic zones, each with their own climate, landscapes and life forms. Despite appearances, these mountains are by no means solid and unyielding masses of rock. They're being forced up by about a centimetre a year. But while they're being uplifted, other natural forces are also wearing them down. You don't have to be here for very long to see the rockfalls and avalanches coming down that are slowly and continually eroding these mountains.
The ongoing evolution of this young mountain range make it one of the most dynamic environments in the world. A perpetual tension between creation and destruction.
Erosion is an enormous factor here. These mountains have been pushed up like a wall right in front of the westerly airstream bringing moist air onto these peaks and raining down at least 10 meters a year on the western slopes. The effects of all this rain, the wind and the glaciers is a powerful erosive force, and without it, these mountains would be an astonishing 20 kilometers above us, soaring right up into the stratosphere.
The evidence of erosion can be seen everywhere. The walls of these valleys reveal a remarkable story dating back several 100 million years.
Geological studies have revealed the fascinating journey that a single grain of sand can go on from here. First, it was eroded from ancient granite mountains and deposited on the sea floor. Seafloor spreading took that grain of sand into a subduction zone where it was buried very deeply, transforming into rock.
Over many millions of years, the rock was uplifted to form a new mountain range, which in its turn will be worn down in an endless cycle of creation and erosion. A powerful force in the process of erosion is water in all its forms. Rain, snow, ice, and fast-flowing rivers. And the same water that wears down the mountains. For most of the last 85 million years, the landscape of New Zealand was totally different to what we see today. When Earth's tectonic plates started moving, the supercontinent of Gondwanaland was torn apart. New Zealand sank below the primeval ocean until it was thrust to the surface around 5 million years ago. The same forces that created the Southern Alps will continue to shape the landscape for millions of years to come.
As well as the uplift caused by the collision between the Australian and Pacific plates, there's also been sideways movement along the plate boundary.
Over 15 to 20 million years, these plates have moved 480 kilometres.
We know this because mountains in the northwest and southwest of the island contain rocks that were once in the same place.
In geological time, the forces of plate tectonics are incremental. But in contrast to the results of tectonic plate movement occurring over millions of years, the far-reaching impact of erosion is visible on an almost daily basis.
Another factor eroding the mountains is rainfall. The New Zealand Southern Alps are the only significant barrier, apart from the Andes, to the moisture-laden westerly winds that circle the Southern Ocean.
On reaching the Alps, the air is forced to rise. It cools and condenses, dropping huge amounts of precipitation onto the west coast and mountains.
That rain also feeds these amazing waterfalls.
The impact of water in all its forms can be seen everywhere. Snow, ice, and fast-moving rivers have gouged, shattered, and worn the rock to create the alpine landscapes.
Evidence of the vigorous erosion can be seen right here, with these impressive scree slopes and the extensive boulders and gravels that make up the beds of the larger rivers and gullies. It all contributes to this spectacular landscape.
Erosion is a gradual process. However, occasionally sudden events can cause instant change.
Erosion in these mountains can happen staggeringly fast. On December the 14th in 1991, there was a party of climbers preparing to climb Mount Cook when they heard a huge roar coming from above them. When they looked up, they saw orange sparks flying as rocks crashed into each other and hurtled down the mountainside. The peak of the mountain was 3,764 meters high at that point. But New Zealand's highest peak lost 10 metres in this avalanche, which then hurtled down the mountainside at 200 kilometres an hour. It surged across the plateau here and cascaded down the Hochstetter icefall all the way onto the Tasman Glacier below, and it even climbed the far side of the glacier by about 100 metres.
The avalanche on Aoraki Mount Cook had an immediate effect on the alpine landscape. Over millennia, immense force and incremental movement cause massive geological change.
So what are these mountains actually made of? Well, if you look in the cliffs behind me here, you can see vertical layers of brown sandstone and dark streaks of mudstone between them. These layers, amazingly, were once upon a time laid down horizontally in the ocean floor long before New Zealand existed.
The alpine environment today is home for a diverse range of wildlife and vegetation.
The alpine zone is the area in our mountains above the tree line. Because of the extreme weather conditions, plants and animals have to be tough and well adapted to survive here. Amazingly, about a fifth of New Zealand's plant species, 500 of them, live exclusively in this alpine zone. They cling to a wide variety of environments, such as scree slopes, riverbeds, boulder fields, and even bare rock surfaces. Two of our unique alpine birds are the mischievous kea, New Zealand's alpine parrot, and the gorgeous little rock wren. They have made these mountains their home.
Science helps us understand how New Zealand was created. Ongoing research is providing fresh insight into the forces and impacts of continental plate tectonics.
So this is what plate collision looks like in the southern Alps of New Zealand. And with Aoraki Mount Cook behind me here, it doesn't get much more dramatic than this. In the North Island of New Zealand, the Pacific plate is actually being pushed underneath the Australian plate in a process we call subduction. But here in the Southern Alps, the two plates are simply squeezing each other, and that's shortening the Earth's crust, a bit like a rug being rucked up against a wall. It's thought that in the last 10 million years, the Earth's crust has actually been squeezed and shortened by 90 kilometers in this way.
Most of this deformation presents as rock failure or slippage along fault lines. But some rock is more elastic and generates folds in the landscape. Folding is a natural consequence of tectonic collision. The bulldozing by the Pacific plate as it pushes relentlessly against the Australian plate. In effect, New Zealand is being squeezed by a massive tectonic vice.
As we follow the alpine faults to the southwest, we come to Fiordland, and here the geological situation changes. We have the huge Australian plate diving down underneath the Pacific plate. What this means is that with these fast rising and fast eroding mountains, there's a spectacular example of the forces at play beneath New Zealand.
The Southern Alps are integral to Māori beliefs and cultural identity.
Aoraki Mount Cook is our Moka Ariki, our paramount mountain, and also our tipuna, who came down with his brothers to visit his father, Raki, the Sky Father, and his new wife, Papatuanuku, the Earth Mother. When it was time for the brothers to return to their celestial home, Aoraki recited special incantations to lift their waka up into the heavens. Unfortunately, he made a mistake and the waka came crashing back down into the sea. The brothers clung to the side of the waka, eventually clambering back on board up to its highest peak, and they were stranded. Eventually, over time, they turned to rock and became the Southern Alps. Aoraki Mount Cook, its highest peak.
The story of the mountains and the reason New Zealand's landscape is so diverse and visually compelling would not be complete without examining another force of nature, glaciers.
As well as the enormous tectonic uplift of the Southern Alps and the erosion wearing the mountains back down, there's another factor at work: ice. Glaciers have had a huge role in shaping this beautiful landscape, as we see here on Fox Glacier.
Glaciers are formed by snow. When the temperature is cold enough and sufficient snow falls in the high mountains, it compresses and hardens into ice, which is then pulled by gravity, slowly sliding downwards, gouging out the rock and carving valleys.
A bit of tech that we use is this high-precision GPS system. I use this to measure how fast the glacier flows and how quickly the ice is thinning. Earth has undergone numerous periods of warming and cooling, with the cooler periods known as glaciations or ice ages. The most recent ice age was about 2.5 to 3 million years ago. During this time, temperatures in New Zealand were about 4.5 degrees colder than they are today.
Snow steadily builds up on the mountains, layer upon layer, compacting into ice and creating huge glaciers that flow down the mountains towards the ocean. During the ice ages, glaciers covered much of New Zealand, and today there are still over 3,000 in existence.
Glaciers act as giant conveyor belts. They transport rock debris from high in the mountains and dump it at lower elevations in ridges we call moraines. These moraines form at the sides or flanks of the glacier and at the very front.
As the glaciers slowly grind down the valley, they erode the rock beneath and on the sides, producing moraine and transporting it down the mountain. What was once a V-shaped river valley becomes a U-shaped valley carved by ice.
When a glacier is melted away, these moraines or ridges are left behind. At the peak of the last ice age, the Fox Glacier was huge. It filled this valley and flowed down towards the coast. We know this because moraine ridges, hundreds of metres high, extend right out towards the sea.
During the ice ages, immense glaciers and ice caps formed and retreated many times. Few deposits of early glacial periods survive in New Zealand. They were usually overrun and destroyed by subsequent glaciers. Glacier debris lying amidst the fast rising mountains was quickly carried away by powerful rivers.
As glaciers recede, they not only get shorter, but they also get thinner. This has a flow-on effect to the slopes that surround the glacier. It makes them more prone to rockfall. To learn more about these processes, we are using unmanned aerial vehicles to photograph the slopes. We photograph the slopes and then create a three-dimensional model.
Heather's research enables scientists to estimate the amount of rock falling onto the glacier. As the glacier retreats, The valley created by the ice reveals the rock and evidence as to how and when it was shaped.
Glaciers are amazing indicators of climate. They represent a delicate balance between the amount of snow falling in the top of the mountains and the ice melting away at lower elevation. The ice I'm climbing here on Fox Glacier started as a tiny snowflake high in the mountains, and it's taken it about 60 years to get to this point.
Glaciers are exciting environments to explore and are impressive evidence of nature's power.
Glacier tourism is hugely important to the local economy here on the West Coast. Over 400,000 people come to see the glacier every year.
As the ice retreats, foot access to the glacier is becoming more challenging, and helicopters are increasingly used to ferry people to the upper regions. On the eastern side of the Alps, at the foot of the Tasman Glacier, a large lake has formed.
We're here on Lake Tasman, trying to understand why this lake goes through sporadic periods of rapid expansion when large numbers of icebergs are breaking off into the lake, followed by other times when things are much quieter. Lake Tasman didn't exist 40 years ago. It started its life as a small collection of melt ponds up on the surface of the glacier. The water in the lake, although cold at only 2 to 4 degrees Celsius, is still much warmer than the glacial ice. So the water actually melts the ice, undercutting it, causing large icebergs to break off into the lake. We call this process iceberg carving. We're using a remote-controlled jet boat to learn more about the processes that control iceberg carving. The jet boat's equipped with a deep water echo sounder, high-precision GPS, and we use a wireless modem to transmit the information about the water depth back to us on the boat.
The ice is dangerously unstable, and sensors on the jet boat collect data to assist Heather's research. Global climate change is melting glaciers worldwide. The retreat and diminished ice thickness of New Zealand's Franz Josef Glacier is starkly revealed in these two images. One was originated in 1880, the other 2015. Maori oral tradition explains the unique glacial environment, bringing to it human form and emotion.
Not far from Fox Glacier is the Franz Josef Glacier, known to our people as Ka Roimata or Hini Hokitere, the tears of the Ice Maiden. Hini Hokitere lived a long time ago, and she loved to explore and to climb the alpine regions. Her lover Wawe often struggled to keep up with her. One day when they were out adventuring, Wawe lost his footing and fell to his death. Hini Hokitere was broken-hearted and wept so many tears that they flowed down the mountains and were frozen to become the glacier. Ka Roimata or Hini Hokitere, the tears of the Ice Maiden.
Glaciers are very important indicators of what's happening to the climate. And it might look like there's inexhaustible amounts of ice and snow here in the Southern Alps. But in fact, there have been huge changes here over recent decades. In 1977, there was an estimated 54 cubic kilometers of ice in the Southern Alps. Since that time, at least 1/3 of it has disappeared. The last few years of this century have seen the warmest years on record, and by 2100 they're set to rise by a further 2 or 3 degrees. This is bound to mean huge changes to our environment. The big valley glaciers in the Southern Alps each have large terminal lakes at the end of them. These have been expanding dramatically in recent years. Once established, they eat away at the ice in an unstoppable runaway effect. And this has actually caused most of the ice loss in the Southern Alps in recent years.
In the North Island, Ruapehu has a permanent snowfield from where 18 small glaciers originate. An active volcano, Ruapehu occasionally erupts, emitting ash and rock debris. The combination of dark ash and volcanic heat accelerates the melt process.
The distinctive shapes of our high mountains are all sculpted by repeated landslides, glaciers and rivers. Landslides occur widespread throughout New Zealand, wherever there are hills or steep slopes, but they're not normally as spectacular as those that we see here in Aoraki National Park. Nevertheless, our mountains have been shaped by deep subterranean forces, weather and ice.
New Zealand was created by titanic forces beneath New Zealand. And still today, the land is reaching upwards, pulled back by erosion, eternally seeking a balance between creation and destruction.